Okay, so today we're going to talk about the answer to that question of how whether or not the order of or how you wire things up is going to affect the resistance. So we're going to talk about it in terms of this equivalent resistance. You could also think of equivalent resistance as the total resistance of the circuit. But not always are you finding the total resistance of the entire circuit, sometimes just a part of the circuit. That's why we call it equivalent resistance. So if I have like 3 or 4 resistors wired a certain way and I want to replace all of those resistors with one resistor, what size resistor would I need? That's what equivalent resistance is all about. We often call this Kirchoff's rules. What we're going to be talking about today is not the actual Kirchoff's rules. We're going to be kind of going into the end result of those because the actual rules, the wording of them can be kind of confusing. And so we're just going to get into the end result of what those rules are. So we're going with equivalent resistance. Yay! So let's start off by talking about series circuits. So I'm going to draw a little schematic of a series circuit for a second. We have a resistor, another resistor, another resistor. And what is this thing?
Battery.
A battery cell. All right, so there's resistor, resistor, resistor. So I'm actually going to label them R1, R2, and R3. Now, as the current comes out of the battery, it leaves the positive side, and it goes this direction. Now, does it have to go through R1? Yes. So it goes through R1, and then it goes around. Does it have to go through R2?
Yeah.
Yes. And then it goes through R2, and then it comes around. Does it have to go through R3?
Yeah.
Yep. So then it keeps going around back to the battery. Okay? So since there is only one path for the current to follow, the current has to go through every single resistor. Okay? Now, if you think about the current like the electrons walking through a hallway, and there are people walking through a hallway. With a series circuit, the hallway is only wide enough for one person, right? So let's say you're all walking down the hallway, and as you're walking down the hallway, the people in front of you are going a certain speed. Can you go faster than the person in front of you? No, because we're talking like this is a hallway situation where you can't go around them. So you can't go faster than the person in front of you. And then let's just pretend for a second that you're all attached by strings. If the person in front of you starts going faster, what's going to happen to you? You go faster. So think about that when you're talking about the electrons moving through a series circuit. They're all traveling in the same path, and so they all have to travel at the same speed. All right? They can't go faster than the ones in front of them. They can't go around them. So the current or the flow of electrons, the flow of charge, how many charges pass per second, is the same at all points in that circuit. If one part slows down, the whole thing slows down. If one part speeds up, the whole thing speeds up. All right? So they have to go at the same speed. So what that means for us is in a series circuit, my total current of the circuit is constant. Doesn't matter how many things I have in my circuit, the total current is constant in a series circuit because it has only one path. Okay? Make sense? So, that is helpful to know. Now, if I think about the voltage, the potential difference, so if I know that all of my currents are the same, and I know that V equals I times R, then the voltage at point 1 is the resistance of 1 times the current, correct? And the the potential difference of 2 is the resistance of resistor 2 times the current. So if these resistances are different, will their voltages be different? Yes. All right? But there's one very important thing. Where does all of the potential of the circuit come from? It comes from the battery. So can my difference in potential here to here be different? So what's going to happen? Okay, let's start over. I have potential energy that leaves the battery. We're going to pretend, for our purposes, we pretend that wires have no resistance, so it doesn't lose any energy until it hits that resistor. All right, once it goes through the resistor, it's lost energy. So there is a difference in potential. Then it goes around and it comes to this resistor. It goes through that resistor and it loses energy. So there's another difference in potential. And then it comes around and it loses more energy. So there's a difference in potential. And then it's back to the battery. Okay? So it has, say, 300 joules of potential energy here. When it gets all the way back around, it's lost all that potential energy. So the total difference in potential has to be the same as the drop there, the drop there, and the drop there added together. So if you want to think about this like a water in a pipe situation again. Let's say I have water in a pipe, and right here I have a pump. The pump is like the battery. It's what provides all the energy, all right? And the pump, let's say your pipes are situated like this, okay? All right, so the water is going to be pumped from the pump, and up here at the top it has potential energy, right? Then it's going to reach a resistor, and it's going to drop. That potential is going to drop. It loses energy. And then it's going to flow to the next resistor, and it's going to drop. It's going to lose energy. Then it's going to flow to the next resistor. Then it's going to drop. And then it's going to lose energy, and then it's going to come back around. And so this section right here represents the battery. It's the pump. So there's a difference in potential from here to here, right? There's a difference in my potential energy of the water. So the difference in potential energy from here to here and the difference in potential energy from here to here and from there to there, all of those differences have to add up to that total difference, right? Same thing with the battery and with a series circuit. So whatever my battery potential is, all right, the potential difference of the battery or source, if it's not a battery, if you have a DC power supply or something, so you could call that the total voltage, is going to equal the sum of all of the individual voltages. Now, why do I have the little dots at the end?
Because it goes on forever.
Yeah, it depends on how many. Most of the time we're only going to have 2 or 3 things in the problems that we do. But if I had 52 resistors, I'd have V1 plus V2 plus V3 all the way like that. Okay? So, any questions on that? All right, now, let's talk about the resistance. If we already said that the current has to go through this resistor, right? So if this resistor has a low resistance, the current's going to fly really fast. But if this resistor has a high resistance, it's going to slow down, which means it slows down everywhere. Does that make sense? So that means that whatever the resistance here is, plus the resistance here, plus the resistance there, is going to tell me the total resistance of the circuit. So if I have one big resistor and a bunch of little resistors, they're going to kind of add together. Okay? So the end result here is that my equivalent resistance, all right, is the sum of all of my individual resistors. So if I wire something in series, then each thing that I put in that circuit is going to increase the resistance of the circuit. And if I increase the total resistance of the circuit, I'm going to be decreasing the current because of V equals IR. If I increase the resistance, then I have to decrease the current of the circuit. Does that make sense? So that is a series circuit. Any questions? Okay, so parallel circuits. Let's draw one of those real quick. We have our battery, resistor, resistor, resistor. So there we go. And again, let's label them R1, R2, and R3. And this is my total voltage or my battery. Now, let's talk about the current here now. When the current comes out of the battery, comes around, it reaches this point. What does it do? When it gets to this junction right here, what's the current do?
Split in half.
Okay, so the current does split. Some of it's going to come this way. Some of it's going to go this way. All right? And when it reaches this point, it's going to split again. Some's going to go that way, and some of it's going to go this way, around like that. So does the current have to go through resistor 2 and 3? No. Does it have to go through 1 and 3? No. Does it have to go through 1 and 2? No. It has options. Okay? That's the whole point of a parallel circuit, is it could go just this way. It could go just this way. It could go around that way. So using the hallway analogy again, think about it this way. If you're trying to get to class and you're walking through the hallway and it's really, really crowded in the D300 hallway, then you take a little path on a different way and go down a less crowded hallway, right? Does that make sense? Yeah. So you're going to take the path of least resistance. You're going to take the path that's going to allow you to get to where you need to go the fastest. Okay? That's what electricity does. So it's going to split. Now, if all three of these paths are open pathways, some of the electricity is going to go through. Just like if you look at the hallway during pass period, there's always somebody in one of the hallways. Some hallways have lots of people, some hallways have very little, right? So the current is going to split. Now, how much comes out of the battery is determined by the total resistance of the circuit and the voltage of the circuit. Ohm's Law, V equals IR. That's what helps us determine the total current. Now, once that total current comes out of the battery, when it gets here, some of it has to go this way, some of it has to go that way. But can I have more current in R1 and R2 together than I had total? Right? If you think about it in terms of like people walking through the hallways, once every student walks into the hallway, can I have more students in this hall and this hall added together than I have total students? No. And that's the whole point of this situation. I cannot have more current going through 1 and 2 than I have right here. Okay? So the total current has to add up. That's the difference here. Your total current in a parallel circuit is the sum of the individual currents. You notice that that is different than the series circuit. In the series circuit, the current is constant. In a parallel circuit, the current adds up to your total current. The current in each branch is going to add up to the total current of the circuit. Okay? This is based off the law of conservation of energy and conservation of charge. You cannot have more charge in the branches than you have total to begin with. Now, let me ask you this. Back to the situation of potential difference. If I have a battery, it's got the potential, right? So when it gets to here, it's going to go through this resistor and drop. But isn't that resistor essentially connected directly to the battery? And what about resistor 2? Is it connected directly to the battery? And resistor 3 is connected directly to the battery also, right? Which means each of those resistors is getting the full potential difference of the battery. So in a parallel circuit, your potential difference is constant. because they are all essentially connected to the same point. So the difference in potential from here to here is the same as the potential difference from here to here, and the same as the potential difference from here to here. So if you looked at it in terms of the water pipe analogy again, this would be like having pipes that are shaped like this. And then my pump is right here. And so the water comes out and it's going to drop all the way down and then get pumped back up. Or it's going to go this way, drop all the way down, and then go pumping back. Or it's going to go this way, drop all the way down. So the total drop is the same in all parts of the circuit. Make sense? Now, what this means though is because the resistance is less, since something takes the path of least resistance, what this means is that your total resistance happens to be less than any individual resistor. All right, this is a funky equation. And we're not really going to get into where it all comes from, but 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So basically the reciprocal of my equivalent resistance is equal to the sum of the reciprocals. That's the way that you would actually talk about this. So again, that's kind of a funky equation. So let me see if I can give you an example situation. Let's say resistor 1 had a resistance of 2 ohms. All right, so I would do 1 over 2 ohms. And resistor 2 had a resistance of 3, well, we'll say 4 ohms. Make the fractions a little easier. And say resistor 3 had a resistance also of 2 ohms. Okay? Well, then I have to add these together. 1 over 2 plus 1 over 4 plus 1 over 2. So I need common denominators. So this becomes 2 over 4 plus 1 over 4 plus 2 over 4. So that's 2 plus 1 plus 2, which is? That's 5 over 4. Okay? Now, that's not my answer, because this is 1 over the equivalent resistance. And this is the mistake most people make when they solve these problems, is they do this part correctly, but then they give me this as the answer. When 5 over 4 is only part of the answer. All right? 5 over 4 is 1 over our equivalent. So my equivalent resistance is the reciprocal of that, 4 over 5. Okay? And then you actually plug it into your calculator and get the actual decimal number for it. But you have to remember that when you plug this in, you're solving for 1 over r when you just do the fraction. I don't want 1 over r, I want r. So you then have to take the reciprocal of your answer. Okay? So, those are the equations for Kirchhoff's rules. And let's see an example. So I'll go ahead and give you a couple seconds or so to draw this in your notes, because you're going to want to have this as an example. Okay, so as we do this, the most important thing for you to remember is Ohm's Law. Ohm's Law applies to every part of the circuit as well as the entire circuit. So let's go ahead and write in the stuff that we know onto our picture. For my battery, I know that the voltage is 60 volts. And I know the voltage of resistor 1 is 25 volts. I know that the value of resistor 2 is 15 ohms. and I know that the current total, so that I'm going to write my total current here with the battery. My total current is 2 amps. Now, first off, what type of circuit is this? It is a series circuit. So I know that my total current is constant because it's a series circuit. So that means my current in each one of these locations is 2 amps. And that's a 3, not a 2. Okay? So if I know my current and I know my resistance or my voltage, if I know any of these, 2 of these 3, I can figure out my total, right? Or figure out the third one. So if I know I equal and V, can I solve for R? Yeah, using this equation. R is V divided by I. So 25 divided by 2. It's 12.5. All right. Now, I know I and R here, so my voltage here is going to be, and I'm actually going to go ahead and write R1 here. This is 12.5. My voltage, V equals I times R, well, that's 15 times 2, so that's 30. All right, so my voltage through 2 is 30. Now, with R3, I don't know voltage and I don't know resistance. So I only know one thing. I know the current. But I know that my total voltage has to add up, right? That was that equation for series circuit. The total voltage in a series circuit is V1 plus V2 plus V3. So if I know my total voltage is 60, then 60 has to be 25 plus 30 plus something. All right? So 30 plus 25 is 55. So that means this has to be 5 because they have to add up to 60. So that means my voltage here is 5 volts. Okay? Which means that I have to have a resistance of voltage divided by current. 5 divided by 2 is 2.5. Okay? That makes sense? Now, if I did all this correctly, then my total resistance should equal resistance 1 plus resistance 2 plus my resistance 3. I don't know why I put a 3 there, because I was saying 3. So 12.5 plus 15 plus 2.5. Well, 12.5 plus 2.5 is 15. And 15 plus 15 is 30. So it works out. That makes sense? I'm just using those 3 equations I gave you for a series circuit and Ohm's Law. Cool? Now let's see how we do it with a parallel circuit. Again, I'll give you a few seconds or so to draw the circuit and label it and write down your given information. All right, so now this time we know the voltage of resistor 1. So we know the voltage here is 30 volts. Does that tell us anything about the circuit? It's a parallel circuit. What do we know about the voltages in parallel? They're all equal. So that means if the voltage or the potential difference in resistor 1 is 30, then the potential difference in my total circuit is 30. The potential difference of resistor 2 is 30, and the potential difference of resistor 3 is 30. So they're all 30 volts. Okay? If I know resistor 2 is 15 ohms, and I know that its voltage is 30, and I know V equals IR, then the current through resistor 2 is the voltage divided by the resistance. What's 30 divided by 15? 2. So the current through resistor 2 is, I don't know why I just wrote that, 2 amps. All right? So it also tells me that my total current coming out is 18 amps. And that 18 amps is going to split. Some of it's going to go this way. 2 amps is going to go down that way. And 10 amps is going to go through resistor 3. That's what the thing on the side tells me. So if 2 amps goes through resistor 3, or 2 amps goes through resistor 2, 10 amps goes through resistor 3, that's a total of 12 amps. So how many amps have to be going through resistor 1? 6. Because these 3 currents have to add up to my total current. Okay? So now I know that this is 6 amps, 2 amps, and 10 amps. Now, if I know that the current and the voltage, I can find the resistance. So 30 volts divided by 6 amps is 5. So my resistance for resistor 1 is 5 ohms. All right. Resistor 3 is a current of 10 and a voltage of 30. So 30 divided by 10 is 3. Now, this is where that lovely fun equation comes in, because we're not going to just add these together. The equivalent resistance is 1 over R1 plus 1 over 15 plus 1 over 3. Now later I'll show you how to do this in your calculator, but I've chosen numbers here that give us fractions that are not too complicated to deal with. So we're going to get a common denominator of 15. So to get 5 to be 15, I multiply by 3. To get 3 to be 15, I multiply by 5. So this gives me what? 3 plus 1 plus 5 is 9 over 15. All right? But that's 1 over R, so I have to flip it. So my resistance, R, is 15 over 9, or 5 over 3. All right? Now, just because I'm not using a calculator right now, I'm going to leave it as a fraction. When I have you do this, I want you to actually give me the decimal number. But is 5/3 less than 5? Yes. Is 5/3 less than 3? Yes. What you should notice is when you have a straight parallel circuit like this, your total resistance will always be less than your smallest resistor. Okay? So if your smallest resistor is 5 ohms and you get an equivalent resistance of 30, you did something wrong if it's a parallel circuit. Does that make sense? Okay? Now let's look at one. We've done straight series and straight parallel. What if I have a combination of series and parallel in the same circuit? Okay, so look at this one. Now, this one I have 4 resistors. I'm going to label them R1, R2, R3, and R4. Okay? Now, when you have something like this, you need to separate the circuit into series and parallel parts. You notice that R2 and R3 are parallel to each other, right? So what I want to do is replace them with one resistor. All right? So I need to find the equivalent resistance of R2 and R3. But I don't know R2 and R3, do I? Okay, so I don't know the resistance of R2 and R3, so I can't really find the equivalent resistance. So let's look at what I do know. I know the voltage is 120, I know that R1 is 8 ohms, and I know that R4 has a current of 6 amps. Now, if R4 has a current of 6 amps, notice R4 is in series with the battery. So if it has a current of 6 amps, the battery has a current of 6 amps, which means R1 has a current of 6 amps. So current 1 is 6 amps. All right. Now, does that mean I2 and I3 are both 6 amps also? No. But since it splits right here, all right, the current splits, I know that the sum of the current through 2 and the current through 3 has to equal 6. Because I only have 6 amps going in to this junction, and so I have to have 6 amps coming out. So some of it goes this way, some of it goes that way, but the total there has to be 6. So I2 plus I3 has to equal 6. And my total current is 6 because that's the current of the battery. Okay? They're not necessarily equal, so it's not just 3. Okay? If R2 and R3 have the same resistance, then they would get the same current. But remember, the current's going to take the path of least resistance. So whichever one is the smaller current is the one that's going to work. Okay? So, we have filled in some of that. Okay, so if I know I1 and R1 is 8 and I1 is 6, what's 8 times 6? 48. So I know the voltage there is 48. Okay? Do I know R4? I do know R4. It's 6. And I4 is 6. So 6 times 6 is 36. So I know that that voltage is 36. I'm using Ohm's Law, V equals IR for each situation. Okay? Now, I need to know my total voltage from this point right here to that point right there. And I know that resistor 2 and resistor 3 get the same voltage because they're in parallel, right? Well, 120 has to equal the total voltages of the circuit because it's series, all right? So 48 plus 36 is 84. All right, so I have 120 minus 84 is 36, which means this is 36 volts and this is 36 volts. Because they are in parallel, they get the exact same voltage. Okay? So now, if I know resistor 2 is 18 ohms and its voltage is 36, I'm going to find its current. 36 divided by 18 is 2. So the current through 2 is 2 amps. So that means the current through 3 has to be 4 amps because they have to add up to 6. So now I know the current through 4, and so resistor 3 is, I know its voltage is 36 and the current is 4, so 36 divided by 4 is 9. So now we need to do the equivalent resistance. Before I can do the equivalent resistance, I have to find the equivalent resistance of that section. So I'm going to do 1 over R equals 1 over R2, which was 18, plus 1 over R3, which was 9, or I can rewrite that as 2/18. So this becomes 3 over 18, and that's 1 over R. So I'm going to flip that and make it 18 over 3, which is 6. So the equivalent resistance there is 6. So my equivalent resistance for the circuit is the resistance of 1 plus the resistance of this section here plus the resistance of 4. So I have 8 plus 6 plus 6. 6 plus 6 is 12. 12 plus 8? and that is that circuit. Okay? Okay, while this worksheet is being passed out to you, I'm going to go ahead and draw one of the circuits that's on it, because this one, over the years, I've noticed that this one tends to get people a little confused because of the way it's drawn. So I want you to see it. So I'm just going to call these 1, 2, 3, and 4 instead of R1, R2, R3, and R4. But I want to make sure everybody's paying attention to this, because I want you to see how to redraw these to where they make a little bit more sense. Okay? So, first, I'm going to draw my battery. I'm just drawing the exact same circuit here. I'm going to start with the battery. And if I follow the current, it comes out of here and goes that way. And what's it do at this point right there? It splits. So it's going to come to that point and it's going to split. Alright? If it goes this way, then it goes through R1 and then it splits again. Right? Because it splits right there. Did everybody see that? When it goes this way, it just goes around to R4. So this is the other split. It just goes around to R4. Now, when I get to this split, it's going to go this way. Some of it will go through R3. And then some of it here will go through R2. So we'll call that R2 and this one R3. But eventually, the current that goes here through R3 is going to meet back up with this, right? And all of it's going to meet back up with that. So these are going to meet back up, and they're going to come back around and meet back up with that. And then all of this is connected back to the battery. All right? So it looks really stinking complicated, but remember, you have, essentially, start from the inside out. You have a small parallel circuit. You can use the rules to get that. Then, this parallel circuit is in series with that resistor. And then you have a larger parallel situation. Okay? And then, so you just go through the rules. This is a bit of a puzzle. It is going to take a little bit of thought and processing and some practice. That is your homework. Good luck.